We introduce edit implicit shapes through part-aware generation. Or in short, spaghetti. To get a sense on what we mean by part-aware generation, let's have a look on this sequential editing. The user can select different parts from different shapes or make further local adjustments. On each edit step, the spaghetti model follow the user specifications and synthesize a new implicit shape. Neural implicit fields are quickly emerging as an attractive representation for learning-based techniques. However, so far only little effort has been made towards adopting them for 3D modeling and editing. We introduce spaghetti. Spaghetti is a 3D generative model that learns unsupervised part decomposition of generated implicit shapes. Spaghetti can generate new implicit shapes conditioned on different parts. In addition, with spaghetti, the user can make further local adjustments over the implicit shape by specifying transformations over selected parts. Our network is composed from 3 sub-networks. The first, decomposition network, receives a global shape vector, Z, and outputs a set of part vectors, ZD. The part vectors continue through a mixing network that outputs the mixed embeddings ZM. Finally, we get the implicit shape, in the form of an occupancy network. The occupancy network receives 3D coordinates and outputs their occupancy indicator, conditioned on the mixed part vectors. For mixing between shapes, we want to have disentangled part embedding space, such that each part vector has limited influence on the generated shape. To allow local transformations, each part embedding should hold a separate representation for intrinsic and extrinsic properties. Let's have a closer look on our network architecture. First, we decompose the global shapecode to the distinct part vectors. Then, each vector is projected to the parameters of a single Gaussian, such that the whole set represents a Gaussian mixture model. Previous works have shown the ability of GMM neural networks to learn a consistent decomposition across generated shapes without using explicit part-level supervision. After we extract the GMM, the parameters of each Gaussian are projected back and combined with ZD. We continue to process the set ZD by the mixing network in the form of a transformer encoder. This network transfer information between parts vectors and outputs the mixed embeddings ZM. Finally, the occupancy network is given by a transformer decoder, where a coordinate X attends to the mixed part codes to output its occupancy indicator. The whole network is trained by the ground truth occupancy labels. The part disentanglement in our mid-latent space is achieved by randomly masking different part embeddings. We use the GMM as a self-supervision to relabel the ground truth occupancy indicators. Lastly, we apply random affine transformations that both transform the Gaussians and the query coordinates. This is a key component of spaghetti that later enables to specify local transformations. During inference, we remove the first decomposition network and start with the mid-representation that corresponds with different parts of the output shape. Then, we can replace shape parts by replacing their correspond embeddings with part vectors from another shape. Notice that the transformer architecture can process arbitrary number of parts. For example, in here, we only add handles to our chair. The local adjustments are obtained through the parameters of each Gaussian. The user can apply different transformations that are injected to our coarse GMM representation. We can bring back our decomposition network and randomly sample new shapes. Spaghetti can also randomly generate specific parts, while the rest of the shape is preserved. This kind of generation is feasible, since our latent part embedding is consistent across different shapes. The pre-trained spaghetti model is integrated in our interactive user interface. On bottom, we have a collection of generated chairs. Then, we mark the parts as an input for spaghetti. We can make further adjustments to our new generated shape. Thank you for watching.